page 2 of the reflection and refraction problems. And the first question says, if the index of refraction in a diamond is 2.419, what's the speed of light in the diamond? So I'm going to use that equation in, which is your index of refraction, equals C. And Alexa just told us that that was the speed of light in a vacuum, divided by V. So I'm looking to find V. So I'm going to put in 2.419, which is given up here as the index of refraction for diamond. Multiply that by divide the 3 times 10 to the 8th, which is the speed of light, by the 2.419. And that gives me a speed of light in a diamond of 1.24 times 10 to the 8th meters per second. Now, if you realize that the index of refraction has no units, that's because the meters per second on the top cancel out with the meters per second on the bottom. So you don't have any units for index of refraction. Okay, the next 2 notes I want you to write down, and then I'll show you the simulation of this, is that when light travels from one medium to another one, its frequency isn't going to change. Now, its wavelength's going to change, and its velocity is going to change, but its frequency is not going to change. So when I write a formula, this guy by the name of Schnell, no relation to the guy that came up with a mail system, you know, Schnell mail. He came up with this little formula right here, that N1 sine 1 equals N2 sine 2. We'll talk about what that means in just a second. Let me show you this video. What you're watching here is the top part we're going to say is air, a wave going through air. The bottom part, which is dark blue, is going to be a wave going through water. And as soon as the wave hits the water, what happens? It bends. That's called refraction. But I want you to also notice how the wavelength gets smaller. So let me see if I can, I don't know how to turn it, how do I stop it? How do I stop it? There we go, stop. So if you look at the wavelengths here, up here at the very, very top, they're about as big as my finger. Where down here, they're about as big as half my finger, okay? So this length right here is about 2 times as much as that length right there. So wavelength is doing what? Wavelength is doing what? Going up or down? Decreasing. Very good. Now I'm going to go ahead and let it go again. Okay, I'm closing the ink layer. And as I let it go here, what do you see happening to the speed on top versus the speed on the bottom? Yeah, the speed, the wave on the top is traveling much, much faster than the speed on the bottom. So what you're having here is wavelengths going down, velocity is going down, so frequency must stay the same. Well, the next thing I want you to look at then is, what about index of refraction? If you have a slower speed, what's going to happen to your index of refraction? V gets slower, what happens to N? It gets larger. So therefore, water will have a larger index of refraction than air. And if you look at those little half sheets I just gave you, look at air's index of refraction, what is it? It's 1. Very good. And if you look at water's index of refraction, what is it? Very good. 1.3. So now I want to relate this to how does a prism sort of work and what causes a rainbow to occur. If I got white light coming into a prism, what's going to happen to the speed of light as soon as it gets in here? It slows down. But all of the frequencies have to stay the same. Well, that means this. If you look at Snell's law, if all the frequencies stay the same, all the colors are still going to be there. But they're going to get bent at different angles. So the one that gets bent the least, which will have the lowest frequency, would be red. So red is going to come on out like this. The next color you would have would be orange. The next color you have is going to be yellow. It's going to get bent a little bit more. The next color you'll have would be green. It's going to get bent a little bit more. The next color would be blue. It's going to get even more. But the color that gets bent the most is, yeah, violet. It gets bent all the way down here. Okay, so if I want to find out what the index of refraction of this gem is and what it's made out of, I'm going to use that formula of N1 sine theta equals N2 sine theta. And since air, the light traveling first through air, what's the index of refraction for air? Let's go to Alexa. 1, very good. What's the first angle, Walter, that it gets that it comes in at, the angle of incidence? 45, so I'm going to put in my angle of incidence of sine of 45. Then when it gets into the gem, I don't know the index of refraction, so I'm going to try to find N2. And then what angle does it refract at, Jonathan? Very good, 21.57. So when you take the sine of 45, which is about 0.7-ish, and divide it by the sine of 21, which is somewhere about 0.35-ish, something like that, you're going to get a number pretty close to 2, or 1.9. Now look on that little half sheet that I gave you, and what is the index? What is the gem that has an index of refraction of 1.9? Let's go to called on lately. Hi, Rikus. Zircon. So therefore, Rikus has just given his significant other cubic zirconium because he cares enough to send the very best. Okay, lastly but not leastly, let's talk about these rainbows and get the rainbow notes again. An angle of refraction of light entering material depends on the wavelength. So the smaller wavelengths are going to refract more. That's why you saw the blues and the purples bend more in the prism. When the light goes through a prism, blue light bends more than red light, and the rainbow forms. The dependence on the index of refraction on wavelength in the forming of rainbows is called dispersion. So when the light gets bent, that's called what? Refraction, but the separating of the rainbow is called dispersion. Now, there's one last thing I want to talk about, and that's the total internal refraction, and that's how you can get these diamonds to light up. It's also used in fiber optic Christmas trees and in cable and all that good stuff. Total internal reflection occurs when the light attempts to move from a medium of higher index of refraction, so like a diamond or glass or something like that, to a medium of lower index of refraction, so the air. So I'm going to show you when my laser goes from the glass up here to the air, how you can get to totally internally reflect. The total internal reflection must occur when the reflection is 90 degrees or at least 90 degrees. Here's the formula for getting total internal reflection. I'm just going to go ahead and extend the page here so you can see it. And get it up a little bit higher. So the sine of the angle with a little c. Now that little c means critical angle. That's going to equal N1 over N2. And what's this little note up here say, Logan? About N1. So therefore, N1 must be the diamond or the glass. N2 is going to have to be like the air. So N1 is always going to be greater than N2. It's going to be what it's coming, N2 is going to be what it's going in, like the air it's going into. So if I want to know what is the index of refraction for, if the index of refraction for a diamond is 2.4, what critical angle must the jeweler cut the stone at to give it a total internal reflection and that brilliant light and color? So I'm going to be looking for the angle. So I'm going to have the sine of the angle equals N2 over N1. What are you going to put in for N2? Let's go to Tyler. 1, because that's air. Where did the light ray come from, Braden? The diamond. And what's the index of refraction for diamond? Let's go to Chase. 2.4. And so when you take the inverse sine of that, it gives you 24 degrees. Now let me show you what happens then at 24 degrees on this cube up here.